Welcome to MarkScheme. Geometric sequences. Everything you need made visual. Take a sheet of paper a tenth of a millimeter thick. Fold it, and the thickness doubles. Fold again. It doubles again. Keep going. And after just 42 folds, that stack of paper would reach the moon. It sounds impossible, but the numbers don't lie. The secret is that we're not adding a fixed amount each time. We're multiplying by a fixed amount. That is a geometric sequence. And by the end of this video, you'll own it completely. Here's exactly what this covers, straight from your syllabus. IB analysis and approaches. Standard level 1.3. The common ratio. The nth term. The sum of n terms. Sigma notation, and the link to exponential functions. Tick all four, and you've got the whole subtopic. One thing you do not need here: solving for the exponent, which needs logarithms. That's 1.5, and we'll unlock it there. In the last video, arithmetic sequences, every step added the same common difference. A geometric sequence is the exact same idea, with one word changed. Instead of ADD, we multiply. 3, 6, 12, 24. Every jump is times 2. So how do you test whether a sequence is geometric? Divide each term by the one before it. 6 over 3 is 2. 12 over 6 is 2. 24 over 12 is 2. Always the same number. That constant multiplier is the common ratio r. And the constant ratio is exactly what makes a sequence geometric. Now a connection worth seeing early. Plot each term against its position. An arithmetic sequence gave a straight line. A geometric one curves upward. The points lie on an exponential. That's the link your syllabus asks for. A geometric sequence is just an exponential function, sampled at the whole numbers. Here's the heart of it. Start with one block, the first term. To get the next term, we scale it by r. The one after that, scaled by r again. Every block is the previous one, stretched by the common ratio. Let me lay out 5 of them, with r equal to 2. Each one is double the last. Now watch what the ratio alone decides. Push r above 1, and the blocks explode upward. That's the paper reaching the moon. This is exponential growth. But drop r below 1, make it a half, and the opposite happens. Each block is smaller than the last. The terms shrink toward 0. Hold on to that picture. It's exactly why, next video, an infinite geometric series can add up to a finite total. And here's the punchline that sets up everything to come. Stack the terms into one running total on the right, the partial sum. As we add more and more shrinking terms, the bar keeps growing, but by less and less each time. It's creeping toward a ceiling, not shooting off. That ceiling is the sum to infinity. But first, we need the exact formulas. Let's build the formula rather than memorize it. The first term is just u1. To reach the second, we multiply by r once. The third, u1 times r squared. The fourth, u1 times r cubed. Watch the power on r. Same pattern as the arithmetic case, just with powers instead of multiples. To reach term number n, you multiply by r that many times, minus 1, because the first term took no multiplications at all. So the nth term is u1 times r to the n minus 1. That power of n minus 1, not n, is the number one slip in this whole topic. Keep it in mind. Now the sum. There's a beautiful trick that dissolves the whole thing. Write out the sum of n terms in full. Then write a second line. The same sum, but every term multiplied by r. Notice that this just shifts every term one place to the right. u1r lines up under u1r, and so on. Now subtract the second line from the first. Look at the overlap. u1r cancels u1r. r squared cancels r squared. The entire middle collapses. On the left, you're left with u1. And on the right, minus u1r to the n. Everything between vanishes. Factor the left as Sn times 1 minus r, and the right as u1 times 1 minus r to the n. Divide by 1 minus r. And there's your sum formula. But this only works if r is not 1. Because if r were 1, we'd be dividing by 0. And these two forms are identical. Multiply top and bottom by minus 1 to flip from one to the other. Both are in your formula booklet. Use whichever keeps the numbers positive. The r to the n minus 1 form when r is bigger than 1, and the 1 minus r to the n form when r is a fraction. Same answer, fewer sign slips. You'll meet this sum in shorthand with the Greek capital sigma. Same idea as before. The bottom says where to start, the top says where to stop, and the expression is the geometric term, u1 times r to the k minus 1, that you plug each value into. Take a small one, sigma, k from 1 to 4, of 3 times 2 to the k minus 1. Let k run. 1, 2, 3, 4. And you get 3 plus 6 plus 12 plus 24, which is 45. And check it against the sum formula. 3 times 2 to the 4 minus 1 over 2 minus 1. Also 45. The notation and the formula agree. Let's put it to work. Easy first. My own numbers, IB style. A geometric sequence starts at 5 with common ratio 3. Find the 6th term. Straight into the nth term formula. un is u1 times r to the n minus 1. So u6 is 5 times 3 to the 6th minus 1. That's 3 to the 5th, not the 6th. 3 to the 5th is 243. And 5 times, that is 1,215. A step up. A geometric sequence has second term 6 and fifth term 48. Find r. Then the first term, then the sum of the first 8 terms. The clever move, divide the two terms, u5 over u2. The u1s cancel, and r to the 4 over r to the 1 leaves r cubed. That equals 48 over 6, which is 8. So r cubed is 8, and the cube root of 8 is 2. Dividing terms to kill u1 is the signature geometric trick. Now back substitute. u2 is u1 times r, which is 6. So u1 is 6 over 2. That's 3. Finally, the sum. State the formula, and since r is bigger than 1, I use the r to the n minus 1 form to stay positive. 3 times 2 to the 8 minus 1 over 1. 2 to the 8 is 256. So it's 3 times 255. 765. Now a real-world one. And this time, the ratio is a fraction. Decay. A machine makes 1,000 units in its first year. But output falls 10% every year. Find the total output over the first 5 years. First, read the ratio. Falling 10% means each year keeps 90%. So R is 0.9, and U1 is 1,000. Because r is between 0 and 1, I reach for the 1 minus r to the n form, which keeps everything positive. Substitute 1,000 times 1 minus 0.9 to the fifth over 0.1. 0.9 to the fifth is about 0.59, so the top is about 0.41. And dividing by 0.1 gives roughly 4,095. This is a paper 2 style question, so round to 3 significant figures. About 4,100 units. Last one, and it runs the machine in reverse. A geometric sequence has first term 4 and ratio 3. And we're told the sum of the first n terms is 484. Find n itself. Set the sum formula equal to 484. 4 times 3 to the n minus 1 over 3 minus 1. The bottom is 2. So this is 2 times 3 to the n minus 1, all equal to 484. Divide by 2. 3 to the n minus 1 is 242. Add 1. 3. To the n is 243. Now, the key recognition. 243 is a clean power of 3. It's 3 to the fifth. So 3 to the n equals 3 to the fifth. And matching the exponents gives n equals 5. That trick only works because the number was a tidy power. If it weren't, you'd take logarithms, which is exactly what 1.5 gives you. Before the exam craft, 2 awkward cases worth meeting on your own terms. First, a negative ratio. Take u1 is 1 and r is minus 2. The terms go 1, minus 2, 4, minus 8, 16. The signs alternate, plus, minus, plus, minus. The nth term still works, but bracket the minus 2. u5 is minus 2 to the fourth. And an even power makes it positive 16. Odd powers stay negative. Second, the ratio equal to 1. Then every term is identical, and the sum formula breaks. It divides by r minus 1, which is 0. Don't force the formula. If r is 1, the sum is simply n copies of u1, just n times u1. A quick special case the MarkScheme expects you to spot. Now the exam craft that separates full marks from nearly. First, the classification move. Before you touch a formula, divide consecutive terms. A constant ratio means geometric. If instead the difference is constant, it's arithmetic. Second, your calculator. Enter the sequence as a list and sum it directly to check your algebra. Third, choose the sum form that stays positive, the r to the n minus 1 form, when r is above 1, the 1 minus form, when r is a fraction. Fourth, a negative ratio alternates the signs, so bracket minus r and watch whether n is odd or even. And fifth, finding n usually needs logarithms. From 1.5, unless the number is a clean power, you can match by eye. Paper 1 wants exact values. Paper 2, 3 significant figures. Finally, the 4 traps. 1. Writing a r to the n, instead of r to the n minus 1 in the nth term. The slip we flagged twice. 2. Using the sum formula when ar equals 1. You divide by 0. If r is 1, the sum is just n times u1. 3. The big conceptual one. Confusing ratio with difference. In a geometric sequence, you divide consecutive terms. To find ar, you don't subtract. And 4. Sign errors with a negative ratio. Minus 2 to the fourth is positive 16, so always bracket it. Dodge these 4, and geometric series is free marks. And that's SL 1.3, fully covered. The common ratio, the nth term, both forms of the sum, sigma notation, and everything from a real-world decay to running the sum backwards for n. But notice, when the ratio is a fraction, the terms shrink towards 0. So what happens if we add them forever? That's the sum to infinity coming up next. For more, that's markscheme.app. See you there.